Okay, so our first step into antiderivatives and integral calculus. What's happening here is, in the first several lessons we showed you how to find the derivative of a function, and now we want you to be able to work backwards. So we're going to give you a derivative and say, what function would this have come from? So before we get into their examples, I'm just going to set something up as a quick example to get us warmed up here. Let's say we had some original function and it was x squared plus 2x plus 3. And let's take its derivative, dy dx. And using the power rule, we get 2x to the power of 1 plus 2, and the derivative of 3 is 0. Okay, no trouble yet, I trust. Let's now forget what that original function was. We'll hide this from ourselves for a couple of days until we don't remember the original. And now the challenge is, here is the derivative. Figure out what this original function must have been. Can you do it? Without memory, can you do it just from looking at what these values in front of us are? Well, for the original function, if this is x to the 1, the term this came from must have contained x to the 2. And if it did, then that 2x to the 1 that we do with the power rule would explain why there's a 2x here. So this 2x term came from x to the second power. This 2 is like x to the 0. That must have come from a term with x to the 1 in it. But it can't have been just x, because the derivative of that would be simply 1. This derivative is 2, so it must have been twice as big. A 2 there would explain that. So our original function must have had an x squared term. That's where this piece of the derivative came from. It must have contained a 2x. That's where this came from. Now here's the trouble. Was there a number here? We know there was. Let's quickly peek. Our original contained plus 3 at the end, but how would we know that? This piece got blown away without a trace when we did the derivative, and so there's no way to get it back. When we do this, if we're honest, we have to say the original was x squared plus 2x plus some, there could have been some number here, but I don't know what it is. A question mark would be a fair thing to put here. What we normally put instead is just c for constant, to say, I'm sure about the x squared, I'm sure about the 2x, and without some more information, I cannot lock down this number. So when you do a derivative, the information about this is lost forever, and it's never coming back. And that means when we work backwards and find the original function, like this, what we call finding the antiderivative, typically you're going to have a plus c on the tail end, indicating that if there was a constant, I would have no way of knowing. So you just put this note to say that, hey, there could be a piece here. So doing this step, we called differentiating, or taking the derivative. Going the opposite way. Oh, and one more thing. When we're doing the derivative, we would write either d or sometimes d dx as symbols for taking the derivative of this and maybe dividing it by dx. When we're going back the other way, we say that we are finding an antiderivative. And the other way that we will sometimes say this is that we are integrating. If you think of a derivative as breaking a curve up into an infinite number of tiny pieces, integrating is putting those pieces back together to figure out what the original must have been. And the symbol for an integration is this elongated S symbol. It kind of looks like the slots cut on a violin. If you write that symbol of 2x plus 2 dx, that would be the question I posed here. This means integrate 2x plus 2 dx, or find the antiderivative of 2x plus 2 dx, and the answer would be x squared plus 2x plus c. We'll explain in a little while why this is called an indefinite integral. There's usually more information around this elongated s, which we aren't ready to talk about yet. So for now, all the integrals that we're doing are indefinite, and we'll expand on that in a bit. But for now, that's probably enough for us to get into these examples. Let's see what we can do with these. Clear some space. So The first one is, if 6 is the derivative, what was the original thing? So if we have dy dx is just 6, I'm going to do this a kind of hand-waving way, and then I'm going to do it with a formal rule, and you can decide which one. Actually, I'll do them all the hand-waving way, and then I'll show you the formal rule. You'll see which one you like better. The antiderivative of this, or the thing that we started with, must be 1 power higher, so it would have to have an x in it, and the derivative of that would just be 1, so throw in a 6. The derivative of 6x would be 6, so this would be our antiderivative. And don't forget, there could also have been a constant. If our derivative is x, if the derivative is x, the original function must have been 1 power higher. But if you do the derivative of this, you should be getting 2x. We're just getting x, which is half that big. So the way to explain that would be, there must have been 1/2 or 0.5 out in front of here. Now when you do the derivative, you do 2 times 1/2, they cancel. You get x to the 1, and that's exactly what we ended up with. So this is our antiderivative, right? No, it's not. What did I miss? Plus c. Remember your plus c's. We will always ding you half a point for forgetting your plus c. There will be no mercy for those who forget the plus c. Last one, x squared. X to the 2. Well, if the derivative is x to the 2, the original function must have contained x to the 3. But if we do the derivative of this, we get 3x squared. That's too big. There's no 3 here, which means there must have been a 1/3 parked out in front of here. Does that work now? If we take the derivative of this, we get 3 times 1/3. That cancels. X to the 2. That's exactly what we have here. And you probably remembered this time, plus c. So that's the kind of loose eyeballing it way to do these. Now, here's something a little more rigorous, which you may or may not like. If you think about how the power rule works, if you have x to the nth power and you take its derivative, what are the steps? You multiply by the power of n, so you get n x to the, and then you cut this power down by 1. So the steps are multiply by the power, and then reduce the power by 1. Those are the steps that you take when you are doing a derivative. If you were undoing these steps, what would you do? If you had running this in exact reverse, what would you have to do? Well, you do them in the opposite order, first of all. You would have to undo this, reducing the power by 1. So the first thing you would have to do is increase the power by 1. And then where originally we multiplied by the power, to undo that, you would divide by the power. So the formal steps for doing an antiderivative are, assuming it's a polynomial, are increase your power by 1, then divide by the new power. Let's see how that works with these. Okay, this first derivative is 6x to the 0th power. So increase the power by 1, that gives us x to the 1, and then divide the result by the new power of 1. That gives us 6x, which is exactly what we had before. So yep, that worked. Remember your plus c. Here we have the derivative is x to the 1 to start with. Increase the power by 1. Now you have x squared. And divide by the new power. So you can either put this over 2 or you can write a 1/2 in front of it. And that is indeed our antiderivative, so it worked again. Here we start out with x to the 2. Increase the power by 1. Instead of x squared, we now have x cubed. And divide by the new power. You can write a 1/3 out front or put the whole thing over 3. All right, so simple derivatives you probably can just eyeball. More complicated derivatives, follow these steps and it'll work every time.